Horrible.
Yeah.
Yeah. Okay.
Yeah.
Yeah, come back.
So let's start today's discussion. Good morning and good evening, everyone. So today we are gonna discuss about questions about lecture 5. So it is related to the external and open boundary forcing. So before the class, I have received several 4 questions, and I will show them here. So wait a second. Let me first share my screen. This one. Yeah. So the first question is from Junyong. So Junyong, would you please to uh, talk about your question? So we will let everyone read their question first, and then Dr. Chen and I will answer them one by one. Okay. So first from Junyong.
Yeah, thank you. Okay. Hi everyone. So in this lecture, it introduced the idealized case to quantitatively check how the wind stress option affects the FVCOM results. So the on the screen, so that is the inlet grid, and their x-axis is the open boundary where the S2 tidal forcing is applied and wind comes from the north. So here it compared two wind stress options. It's called LP 9081 and TY 2001. So from the results, the TY shows almost twice larger CD than LP, and the wind stress is also much larger. So we can know that the drag coefficient and wind stress change a lot depending on the options. But the wave field, LP, CP, and HS from the right side did not change much between the two cases. So, however, the surface elevation changed quite a lot. So, if you see the right one compared to LP, the upper region is lower than LP, and near the inlet exit, we can also see some differences. So I'm not clear that which factors, so what caused the surface elevation to change like this. Yeah, that's what I want to make sure. Yeah, thank
Okay.
you.
So I think this question, I think Dr. Siqi Li can answer the question. He
Mm-hmm.
did he did a similar test before. He can show you, but I don't think it's a we find a so large difference like you saw here. But later she can show you. He can answer the question. Okay.
Mm-hmm.
If after he answer, I can if you need I can add something. Okay.
Yeah.
Good.
So So second question is from Aizong. So Aizong, would you please
Mhm.
say something about your question?
Yes, thank you. Hello, everyone. I have two questions that I think both of them
Right.
is related to the resolution. One of them is vertical resolution, and another one is
Mhm.
related to the horizontal. When we consider the precipitation and evaporation forcing in the sigma coordinates,
Mhm.
I wanted to know that the practical criteria
Mhm.
to propose to decide whether the near surface vertical resolution is it fine enough to avoid artificial density gradient, and is it for example rule of thumb criteria to consider or not. And another one is for the river point source, that when the mesh refinement is essential, instead of just relying on advection and like TVD or MP data, and how we can check the reasonable output at the final stage. Is there any criteria for that, like post-processing criteria or not?
Okay, this question later I can answer. Also, Professor Lee can introduce some new method we developed recently. Now we have not released some method, but I can answer question that later. Professor Lee can add some new development how to put the fresh water in the FECOM.
Mm-hmm.
Okay,
Yeah.
good.
So the third question
That's
is
very
from
good question. Yeah.
Yeah, the third question is from the discussion board, from Miwu Park. Miwu Park, would you please read your question?
Okay. Hello. I prepare one question. In simulating tides within a regional model like the East China Sea Shelf, uh, uh, it, it is my understanding that tidal signals result from a combination of waves propagating from the open boundary and
Okay.
thus internally generated by tide generating process. While open boundary conditions around more sufficient for tidal reproduction in small-scale coastal model, I am assert if the same approach provides enough accuracy for larger regional domains. In this regard, I would like to know if it is mandatory to consider the internal tide generated pulse option, the flag 12, for regional model, uh, for regional model simulations. Thank you.
Okay, I can answer the question, okay? Yeah, later, okay?
So the next question is from uh, Jimmy Sale. So would you please read your question?
Yeah, so my question is related to last week question. So I make a model domain just like that, and I additionally to applied Ostia satellite data with SSTGRD method in this model domain. So based on this case is scenario, and I wonder to analytic method for this scenario. So if I make the other scenario with without tide forcing or wind forcing, then I wonder that each scenario's difference is just only uh, affected by some variables, just like tide or not the just or tide or the other variable, or if it is not only affected just only variables, then how can we quantify data simulation effect on this case? Is my first question. And second question is, when we compile to FVCOM, then compile option flex is O0 to O3, but I wonder how we optimize to FVCOM to make more speed is my question second. Yeah.
Okay, then I think I can answer the question one. Dr. Lee and Professor Lee can answer question two.
Yeah,
Okay?
sure. Yeah.
Okay, good.
So any other question? So these are all the questions that I received before the class. So if there is, yes, please, Yunji.
Lee, Dr. Lee, actually, Yunjae have some question, but he didn't send you the question before class, so can he
Okay.
ask?
Yeah, you can show on the screen.
Yeah, please share your screen.
You can show your screen, okay? Oh, Yongji?
Okay,
Yeah.
sorry.
Okay, yeah, Yongji. Do you know how to share screen?
Oh, no. Wait, please.
Okay. You don't have a question? Okay. Okay. So, okay, let's start the answer. Oh, Yongji. Okay, good. Okay. Oh, yeah.
Okay. My question is relaxing nesting in FVCOM. When applying relaxing nesting in FVCOM and planning a sensitive test, I would like ask two questions. In relaxing testing, which has a stronger impact on the result, weight and the weight relaxation weight zone, and in the sensitive test, which parameter should be adjusted first? And question 2 is, when judging whether this set of setting is appropriate, I would like to ask what criteria will you
Yeah, I see your question.
yeah.
Yeah. Okay.
Sorry.
Yeah, no worry. So I see your question, so I think I can answer first, then the Dr. Professor Lee can add, okay? Because he developed the module how to do that. Okay. Yeah. Okay, good. Other question?
네.
If no, we can start the first one. Okay.
I will share my screen.
Yeah, you show your screen, the first one.
Wait a second.
You had a problem, share screen?
I'm sorry.
Your internet?
Now I only have one screen, so it's hard for me. Okay, so here we are. So the first question is from
Yeah.
Junyoung Kim. So here in this slides, there are two different kinds of methods to calculate the drag coefficient on the ocean surface. The first one is LP 1981, so large pond in 1981. So the second one is the TY 2001. So this is a new method from Taylor and Yellen in 2001. And for these two different methods, the drag coefficient, the CD here, is calculated different. So for the first one, LP 1981 CD is dependent on the wind speed. So basically, the higher the wind speed, the higher the drag coefficient. But because this is a really early study, there isn't many observation, especially for the extreme weather observation. So the parameterization is really simple. So you can the relationship between the wind speed and drag coefficient is roughly in this way. So below 10 meter per second and above 25 meter per second, the CD is constant. And within this region, the CD is increasing with the wind speed. But for the second method, the TY 2001, so it considers the surface roughness, the Z0. So in this case, the CD is dependent on the significant wave height, and the LP. LP is
That's right.
peak wavelength. Yes,
Peak
thank you,
wavelength.
Dr. Chen. Peak wavelength. So in this way, you can find that there is a large difference between these two cases. That although the wind field is the same for these two cases, the drag coefficient is totally different, especially behind behind the dam, because the surface roughness at these two regions is totally different. So that is why, since for these two cases, although the wind speed is the same, the wind stress into the model is totally different, and that causes the surface elevation is kind of different between the two cases. So basically, this is how it is caused.
Now I can add some physics inside this answer. The first thing is a larger pond. They developed 1981. This one is completely for the, did not consider unstable weather. They only consider about the barotropical case. Don't consider stratification, okay? Don't track the temperature change, how does this changes, okay? But this formula has been used when the early stage of the model development, the people use a lot of time. Now this one, but however, they don't, this method really depend on, condition, how you set about, change for the different CD, roughly based on a different kind of wind speed. Okay, but this method, we force the code into FVCOM. The reason because this method has been used in the pond, the Princeton ocean model, they use it in the pond. But then based on the study, then we found, you had to consider about, so this method, when the weather is pretty good, they do the pretty good job. But when the storm come here, they always underestimate the storm, okay, the wind stress and the storm. Also, when the weather is not very good, very unstable, a lot of convection happen, its method also underestimate the wind. Okay, so that's why. So we had another method called the Smith method. We didn't include FVCOM. So they consider unstable condition. Okay, that's the reason. We had a coding called a core program. Okay, into FVCOM. So they was determine the skin temperature, the nearby LC the phase interface. So they can calculating determine the unstable condition how the surface roughness is. The most like wind stress really difficulty is to determine the roughness, the CD, because CD is really dependent on the roughness. But like a larger pond model, CD most constant. Okay, but then so then later on, people study about the hurricane, the storm. They find the wave can be really contribution to change the surface roughness. So then they also find, if you don't consider, if you don't consider wave, so you find, wind stress can be significantly underestimated during the storm. All right. So this way they introduce the method calculation just like a new method called Tyler 2001, right? Include the weight, consider the weight change. You can see they definitely changes. When the surface roughness changes, wind stress changes, elevation definitely changes. But the question come out, which one you should choose, right? But you see the source is different. But when you research, you don't know which one you should supposed to choose, right? So that's why I was suggesting when you decide to choose, depend on what study you want to do, right? If you want to study like a earth syntactry, you want to study the stone hurricane, you want to study like stone, you should choose the Tyler 2001. Okay, the reason because when stone come here, they always had a stronger signal way high. They also had a big wave. So surface roughness is much, much rougher than the normal case. That's why, we suggest you choose like a Tyler 2001. But 2001, there has been tested by a lot of people. There are a lot of publication when they do the hurricane simulation. So they found that this method showed a much better results compared with the observation data. Okay, so it depends on the case. Okay, right? Okay. I
Mhm.
hope we answer your question. I
Yeah.
just
Oh,
curious
thank
to know kind of history, what's happened. Okay.
Mhm.
So
Good.
currently in FVCOM, we actually included the other two drag
Yeah.
coefficient scheme. So, but the other two, we need to calculate the friction velocity, the U star. So those two are much more
Yeah.
complicated, but it is also uh, need to be considered if you try
Yeah.
to simulate some extreme weather.
Mhm.
Mhm.
Just like if we can include a core 3.1, the program, the calculation wind stress. Also, they also recalculate the long wave radiation instead of coding. So then also, now it's I think, we have a code 4.0. That's Dr. Lee has added into the FECON coding. So you can use this method, but I think a core program is a pretty good method determine because this has been testing by by long 10 years, heat budget calculation. But this formula used to be developed calculation net heat flux, okay? But they also, this coding, they also use the, kind of, bottom boundary theory to determine the kind of, surface roughness or also wind stress. So you can see that's method, if you don't include wave, for example, right? If you don't include weight, you don't necessary to use the Tyler 2001. You can use the core 4.1, okay, also 4.0. So this way you can consider bottom boundary layer is called skin temperature, skin roughness, particularly for unstable weather condition. That's why that tool is also pretty good. Okay.
Professor Chen, I have additional questions. So I uh, I saw a paper which described that the CD is kind of proportional to the significant wave height if
Yeah.
the wind speed is under than 30 meters per second.
Yeah.
But then after that, if the wind speed is more than 30 meter per sec, then now CD cup is not as grow as much as the significant wave height. It's kind of saturated.
Yeah.
And then
Yeah.
does that included in that core?
Yeah, that's included code. That's a Tyler 201 consider that. Tyler 2001 that consider because this is not like a when you see when the weight continue to drop, then you CT roughly continue to drop. No, they have a cap. Okay, they had a cap. I don't have a picture show you. I think Professor Lee drew a picture before. Show a CD how the function CD to the weight number to the weight length, the peak weight length. You see they go up then flat. Okay, yeah, that's good. But
Yeah.
even if you don't run a weight model, okay, so you also can you can input the weight parameter like you from the FVCOM input file, you can put some there, but then you probably don't get a time dependent variable, changes. But I think I would most suggest don't use the pound LP, the pound, the larger and the pound. Larger pound is the most old method of 1981, but I think if you want to use it, you can use the core, core method into FVCOM, the better. If you don't consider weight, okay. But if you consider weight, I would suggest use the Tyler 2001. Because this method has been testing, but couple also paper they do the hurricane simulation. They found that's pretty good, okay, to resolve the kind of wind stress. Inside, what was stronger wind. Okay. Yeah. Okay.
Okay, so next question.
Yeah, you see my lecture, I was describe the core program method, right? Lecture 5. You can see there how to calculation, so how to, because if we can use the core method, we do the heat budget calculation. Okay, long, central weight and length of heat flux. If you look at WRF model, if people use the weather model, you really can see most of what output the heat budget. When the storm come here, good weather, you don't compare the observation there is pretty good. When the storm come here, so when the storm come, so WRF also other weather model, they always significant overestimate the central and the central heat, also lantern heat flux. That reason we can use the core program rate, calculated. Okay, to do that, that's one can becomes better. Okay.
Yeah.
Okay. So, for the second one, really interesting question. First question, I can answer the question. Be very careful when you get a precipitation evaporation into the model. The reason because when you do sigma coordinate, okay, the water, if you have a uniform, rain or uniform fresh water in the surface precipitation, if you choose sigma coordinate in the surface, not like S coordinate, not the same thickness. Okay, if you have a thickness changing with the topography at the surface layer, just for surface layer. So you put a uniform precipitation water into the first layer, into the surface boundary condition. So, but this water will go to the whole layer for first layer. But however, if the first layer is not a uniform, right? Some region you can cause because you see precipitation into the water direct effect to surface boundary condition for sea level, right? Because the sea level continuous equation delta zeta delta t equal to P minus E divided by the log. That's why the fresh water coming here, he directly affect sea surface level. But then if you had fresh water into the first layer, it's not a uniform, the layer. You put it into the fresh water, they can cause the sea level grading. Supposedly you had a uniform fresh water precipitation into water in the surface. You should not cause any kind of circulation. Uniform, right? Every place. But however, if you don't do carefully, if a sigma consistent, they can cause a circulation. I tested that before. That's why when you put precipitation into the FVCOM, you want to make sure your first layer thickness had a certain thickness, okay? Not you don't necessarily to have a uniform every place, but at least in a slope region, right? Some region you need to have a little bit fine grade. Also make sure it's uniform. That's why I suggest you use the S coordinate. S coordinate, because S coordinate you can guarantee the surface was uniform, right? So this way, but in the shallow water, even you're not a uniform, but you had because you have your first layer in the most deep layer, thick, like a deep, because you get a more layer in the shallow water, you can have a fine resolution, but at least the open ocean side, you must be uniform, right? But uniform is there, so you not cause like a precipitation driving artificial circulation. But a shallow water, you can, for example, I use the 5 meter, okay, for first layer in the open ocean, but first layer. So then in the shallow part, I was less than the 5 meter. That's okay, okay. But however, the larger scale is why you get 5 meter. So you can see you don't cause a larger circulation inside the open water, particularly for the slope region. So you ask me what kind of resolution you need to choose, right? You need to do testing. You do testing. I cannot tell you exactly how many, how many. This depends on case to case, depends on how much fresh water you put in there, right? Because you have a heavy precipitation, have large precipitation. That's dependent. But you can do testing, right? So you change your water resolution. You want to see, you put a uniform fresh water in. You want to make sure don't have a circulation build up, right? Because you put a uniform fresh water, it should at least you should have a very less circulation, not significant circulation build up, right? Probably not exactly zero, but you can see it. But that's a criteria I can give it to you. I suggest you, okay? So this way, so a lot of people don't care. They use sigma current treatment. They just put fresh water in. Oh, they say, oh, this will, they drive in by the wind, by driving, you didn't care. But however, if you don't do carefully, you do have a circulation by precipitation. Now, I did the testing before. I used like a region, right? I used to put a slope, two-dimensional. I just put like a, no, not a uniform, the grade, sigma coordinate, like a sigma 1 coordinate the grade. So then I do find a slope had a circulation come out, right? So this way you can, but I think that definitely you should think it's a layer is better, but it depends on the computation time. Right? You also need to consider how you compute efficient. That's why you do the couple testing. Okay. In our model right now, in our northeast forecast system, so we would choose the first layer. I think it's a 5 meter, right?
Yeah.
But then you can see we use kind of S coordinate, right? In the open ocean, make sure uniform layer. Okay, make sure don't have fresh water issue.
So what is the thickness of the uniform layer do you choose?
Yeah, so the reason
5 meter,
sorry,
5 meter. So
yeah,
what is the thickness of the first layer? Uniform first layer. What thickness?
well,
5 meter?
we use a 5 meter in our model system, but depend on the case. You don't want to use the 5 meter every place. Okay, for our case, because we are region is most of 4,000 meters deep, right? You could not, we want to compute efficient, which is 5 layer, but we use the uniform, right? Use the uniform. We use S coordinate in the open ocean side. The reason because we want to try to avoid this kind of precipitation cross circulation. Okay.
So does that mean not just precipitation, but also how about the heat budget? If
Right?
it's not a uniform sigma, then because of the different layer of the sigma thickness, even though the same amount of heat flux came in,
Yeah.
does that also cause some problem or?
Oh, it depends because the problem is that if you use uniform, you definitely don't cause any problem. But if you use a grid as a like a smaller, no arrow can be become smaller, reduce. Right? This is a question come out is what is the criteria? Which window we should choose, right? How far is it? So that's why, so you need to do some testing, okay? But you have to consider one is the competitive efficiency, one is you have to consider about what is the minimum layer, the signal you need to choose, to avoid that. But however, if you choose the first layer as a uniform, you don't need to worry about, kind of thickness. If a uniform first layer, you don't want to signal because they're all uniform, no matter how signal you choose, right? The uniform, they don't cause circulation, don't worry, right? You see what I mean? But once you're uniform, you don't need to worry, okay? But however, you should sigma corner, you sometimes you not get all place uniform. That's why we suggest you the deep ocean, you use S coordinate, you can guarantee the uniform. Great. But the shallow part, you can have a much high resolution near the surface. They can also avoid the errors. Okay? Right? But again, you try to avoid the try to avoid the artificial circulation driving by kind of precipitation. You choose a uniform layer. That's the first proof you should do that, right? But however, if you that's the reason we use the S coordinate and the sigma coordinate combined together, the hybrid coordinate. In the shallow part we use the sigma, for the region part we use the S coordinate. The reason we want to have a uniform surface, right? To do that. Also for wind stress, same thing. Wind stress is a little bit okay, but not like because the precipitation is like water put in there, right? You have to make sure, but also that's the equation directly related to the continuous equation, right? So that's the issue. But wind stress is a direct driving by momentum equation. That's different. Okay. Do I answer your question?
Yes, thank. Perfect.
Okay. Okay,
Thank you.
good. So now I think for river discharge, I can answer the question first, and then later the Dr. Professor Lee can add. So we have two methods to input the fresh water, like you mentioned. One is called a node point, another called a sear point, right? So when your river discharge is really larger, both methods perform similar. Okay, so if for river discharge very small, I would suggest you use the edge input instead of the node input. The reason because when the freshwater discharge is very small, you put a node input, so water get one node, right, into the water. They don't go to momentum equation. They come to the continuity equation. So then you put water into one node, so this node will because sea level go up, right? Because the fresh water is not very strong, not very larger, right? You put the water in, right? The mass conservation, water conservation changes. That make the sea level up. So they can cause small eddy circulation along the river mouth. Okay, but node method is easy, right? So if you have a very strong river inside the land, so you can put a node, you don't know the method, you don't have a problem, right? Because because it's very narrow, right? You can the water cannot fall the eddy, the water have to go down. But near the coast region, some people put a point source. A lot of people regional modeler, they just put the river as the boundary node, like a coast put a boundary node. That's when the water very small, river discharge very small. Don't use the node. They can cause the eddy circulation around there. Because the node method, they put the water, they go to continuous equation first, then go to momentum. right? But age method, they put the water direct momentum as a flux in. So then the velocity change first. Then after velocity change, they change the sea level. So when the resolution becomes really high, two methods merge together. Okay, but the real problem, two methods difference because resolution is cost. When the resolution cost resolution also depends on where you put the fresh water in. If you most time I suggest the user when you put a river in, don't put it in the coast boundary node. You have to make the river channel, okay, narrow channel into the land. Then put the fresh water in that side. You can avoid a lot of problem. Okay, but if you want to be most like a I know the one and Nova people do the Delaware Bay, Delaware Bay. So they just had because they get a couple river, they just put the river on the one side. Okay, in the river, main river. This is a river here. I just put the mouth over in the one node at the boundary of a river, main channel river. So they found an eddy because it's a river just very small. Okay, if it's very large, they push the water away. Now, around quickly, you don't worry. But the very small, they change the density, right? You put it there because that's fresh water in, right? Fresh water change the density, the change the volume, they can make a sea level go up. Then I have to get some eddy generation there. But eddy generation there, then because it's fresh water, you get density difference. That's why they cause density driving circulation. But this is artificially, okay? It's not a true circulation, okay? So that's the one thing we was doing. So that's why I would suggest you, for two suggestion. One is put a river, make sure you get a river channel, okay, into the land. The second suggestion, when river discharge is larger, okay, you use it either way is fine, but the river discharge very small, don't use node input. Okay, so we also found it very interesting when we do the Changjiang River. So we found that, if we use like a node input in the Changjiang, even we get a channel into the Changjiang, so we find the fresh water come down very slowly. Okay, very slow because they build a sea level. They had to have they build a sea level first, then the sea level put a grading, they push water down. Right? So the momentum method, we find like an age method, they push direct water, like you just like some kind of advection water into there. So the river can be moving much faster. Right? So that's why we find, even for a larger river, we find the method, use this method is better. But now Professor Lee has been developing a new method. So he can introduce you to here, talk about, Okay, so you also another question you cannot see. Okay, we'll go back. Except we'll go back there. Here a question for the kind of MP data. So you will see water point when the grid refinement near river becomes centrally. Yeah, I think it's most just the great resolution. Just you don't necessarily to include all river, but most of the great refinement should be done by the river discharge side. Right? If you put the fresh water in this node, for example, resolution around this side at least like 2 or 3 sides should be the resolution should be high. So this can include because we base our calculation. So if your resolution too coarse, you can cause an overshooting issue. Okay, for river discharge, for when you have overshoot, if you have a refined grade nearby the river mouth, just river source, put a freshwater source inside, you can reduce the overshooting method, make the model more stable behavior. Okay, that's why so you don't need necessarily grade all the grade resolution, at least some cell close to connected to the river output node or the age should be kind of a little bit high, the resolution should be a little bit high, but not necessarily just only the cell connecting to the river discharge side. You need to refine the grade, but not all others. Okay, But once water get into the river, so they can adjust very quickly. Okay. So now I can ask Dr. Professor Lee to give you more answer.
Thank you very much.
Yeah.
So here I want to show everyone something that we have been working on about the new method that Professor Chen just mentioned. So let me share another slide. Can everyone see my screen? So yeah. So for this one, we are developing one new method for the river discharge called the routine informed discharge injection. So in short, reading method. So this method is mainly to working on the case that when the resolution for the land part is really high and the river discharge could be increasing rapidly in a large scale. So in that case, this method will help the model to become more stable and meanwhile to get a better performance. So just imagine in the rainy season, so the river discharge could be increased largely due to the large rainfall. But however, when the large river discharge get into FVCOM model, at the first time uh, it will only stay in one cell or one node. In that case, it will make the surface elevation increase a lot, and there could be a large pressure gradient around that region. So in that way, we developed this method. So for this method, we considered that for the river discharge during one time step, it can travel to a longer distance during this time step. So we just redistribute the river discharge river volume from one single point in the traditional method to a longer distance. So for example, here, if you see this middle figure, so originally all the in our traditional method, all the river discharge will be put in this pink point. So you can all see them here. But in our new method, so we will first find out where the central line of each river are, and then the river discharge will travels along these central lines. So for example here, so this is a river called Nonsuch River in Maine in US. So you can see all the pink lines are the central line for this river. So when the river discharge during one time step is really large, so we will first help the river volume to move the travels along the central points to a longer distance. In that way, it will make the river input increase less compared to the traditional method. So this is what we
Yeah,
are working on called reading.
the key point is method, so because traditional FECOM for all other model, they treat the river as a point source. So then they put the water in only force seal. No matter structure, unstructured grade, they put the river in the fourth tier. But however, when a very strong storm come here, you get a very large precipitation, also like river discharge. So one time step, supposedly the river discharge speed is really fast, river moving really fast. But however, in the model, you only can river move in the one cell for one time step in the beginning. That's why they can accumulate big water in the one cell, right? One cell, they can make the model unstable. But really, supposing, for example, they can go to, if you know the river discharge, the discharge rate, right? You know the width of the river, you know how far they can go during the delta T time. But however, you only put the river in one cell. That's, for coast inundation, you probably get a unrealistic, kind of answer solution. So that's the reason, Professor Lee developed called radial method. This way you can determine how during the one time step how far they can go, right? So you don't want to accumulate water into the one cell. You want to distribute the water along the distance it's supposed to go. So this way, can make water much stable. Also cause inundation. Flooding can be much better compared with the opposition data. This method really useful for, if you want to study for the kind of, flooding, the coastal inundation, so this method you should use, okay? But we will be release the coding very soon, okay? So that if you want to learn the method individually, you can contact Professor Lee. He also can show the slides with your people. You can send the slides, you can learn how this method work, okay?
Does that mean that length should be changed time by time?
Yeah, yeah. But no, we have a module to do that, okay? If you
Yeah,
can
it
have a
is
module to do that.
automatically calculated based on the coding, not manually.
Yeah,
I think
not the
I think
manual. Everything
yeah.
to automated by you. So they help you to find the river, they have to find the central line, not manually, okay? To the order by coding.
I think this is a very good idea, and I believe that this kind of methodology could be also applied to the water gate.
Yeah,
Yeah, because in a Korean,
yeah,
there are many estuary which has a dike,
yeah,
and
yeah,
sometimes they open it.
yeah,
For example, if you remember the Shihua tidal power plant,
yeah,
some kind of there's a so strong discharge happen at the gate.
yeah.
I think it's a similar problem. So
Yeah. So you remember you mentioned you said that they can the gauge electricity the gauge there they open the water so very far away the cargo ship was was had a problem.
mhm,
But then if you look at model, you only put the water as the one, you know, put the water in the one seer at the beginning, like polysol. You cannot put the water very far away. But this method, you can determine how large your discharge rate you have. So you can determine how far they can go in the one-time step.
mhm.
Right. But this whole method, the Dr. Lee, the Professor Lee already developed the code or the module. You can automatically create a node and put a FVCOM wrong. You don't need a manually. We don't do the manual. If you do manual, you're not able to do this work too
Yes,
complicated, right?
yes, yes.
Okay, that's good.
Good.
I think that's the reason I'm happy you answered the good question. We can show you some new stuff. Okay.
Wonderful.
Okay, good. Okay, we can go to third question.
Yeah, let's go back.
Do we answer your question for second question?
Yes, perfect.
Yeah.
Thank you very much.
Okay,
Thank you.
good.
Many appreciate.
Yeah.
Next question is about the tide.
Yeah. The first, I look at your question. You said that do we need equilibrium tide? So that's good, very good question. Equilibrium tide only for larger scale, you need to consider. But for example, East China Sea model, equilibrium tide effect is very small. But however, if you intend the model include South China Sea, for example, South China Sea, because in the East China Sea, most of the ways come away. The propagation in, propagation out. Okay, if you get the boundary condition correctly, you get the tides correctly. Also, you get the percentage correctly and the boundary correct, you get a tide very good simulation. But then you don't need to consider equilibrium tide. However, when the scale is larger, for example, like a South China Sea, like an Arctic Ocean, you do need to consider equilibrium tide. Because when the scales are larger, equilibrium tide really can change the water elevation, tide elevation in the region. Okay, that's why. So you can determine should it be like we use the northeast region, we don't include equilibrium tide. The reason because our most tide energy like wave propagation from the open water to the shallow water. It's the most energy count. So equilibrium tide affection very small in our region, not significant. I didn't mean zero, just not significant. But like South China Sea, the different. South China Sea, you can see they only have a Luzon Strait, right? You go to Thailand Bay over there, they only have two access. Okay, so most of the tide is not like a wave propagation into system. They can equilibrium tide can be really created inside the region. That's why you need to consider like Arctic Ocean. They have two kind of mechanism. One is equilibrium, cause like tide variation. Another one is propagation tide. So this way you have to consider that. But for the region small, for example, you run for estuary. No, you don't need to consider equilibrium tide. Okay, but too small the scale. When the scale is larger, so you consider, but each transient you don't need. But you can do the test. Okay, you can turn on the equilibrium tide, you run the model. So if region too small, equilibrium tide the most very small, right? You always can turn on, okay, but that it probably not affect any solution. But when the domain larger, you can turn on, you can see equilibrium tide do cause oscillation, do cause tide elevation. This way then you need to include that. Okay, that's what I think that's to your answer. Do I answer your question?
Oh, yes, thank you.
Okay, good. Okay, so next one. We don't have much time to the next one is very good question. Okay, so you said if you run this one, your question one, how important data separation send different kind of scenario with time with no, usually depend on what you want to do data assimilation. First things, you don't want to use data assimilation all time to get a solution like your observation. First thing you want to make sure your model can cache like a major variability due to the wind, due to tide, due to all the current input current. You have to use the model to determine that one. Then you find the model can catch the opposition event. Okay, then variability, the special variability. However, they're not accurate enough. Okay, for example, you show the whole tidal elevation. You show about like a wind driving circulation. You see the whole sea level changing, whole the circulation change, temperature salinity. So this way you say, okay, I compare observation. Observation show like a 10 meter, like 1 meter. My model only show 0.8 meter. So this way you say, okay, I want to improve the model. Then you can use data simulation. However, one bottom line is don't use data simulation to create any results you want to see that without get a more robust model. Right? So that's why you should, for example, for tide issue, for example, you run a tide. You don't want to do data simulation for tide because tide is very easy simulation. Tide depends on two things. One is open boundary condition, you make sure it's correct. Another is perimetry. Right? If you get local perimetry correctly, you get a boundary correctly, you should get a very close tide simulation. You don't need to do simulation. Right? For wind driving circulation, if you know how the wind is driving, you should get the wind driving circulation good. But however, sometimes the wind circulation cannot get the result you want because stratification. Right? You put a temperature sensing in the water, you stratification, but you not resolve a very true stratification water in the temperature salinity. They can not have wind driving circulation, right? But they can change the buoyancy circulation. So then you probably don't get the exact result you look at observation. In this time, so you want to do a simulation to improve that. Okay, that's why conditions you have to test the model, make sure your model robust. And I think 20 years ago, okay, I was attend a meeting in Japan. One professor showed the result. He used a two-layer model, simulation the crucial. He said, "No, my two-layer model not resolve the crucial. I do the data simulation." Okay, so then he said, "Oh my God, how no one can use a two-layer model to resolve the westbound current? This is theoretical study, not a real simulation." So you build something is not robust model, you do the simulation, it mean nothing. Right? That's the reason be careful. Make sure you will do the model, make sure your model robust first. Then data simulation only improve your accuracy, not change your dynamics. Okay. Okay. So the second question, I think that Dr. Lee can answer you.
Yeah. So
Professor Chen,
Yeah.
before go to the second question, let me add that first question. I think because I know what he is trying to ask.
Okay.
So the question is, suppose that he build up the reanalysis data using, of course, the data assimilation.
Yeah.
And then from that reanalysis data, he tried to figure out which forcing affected how much. So the question is, for example, let's do the EOF analysis for the geostrophic currents from
Okay.
that reanalysis data.
Uh-huh.
So the question is, how much should I believe? Should we believe that this EOF analysis of figuring out that this portion is from the current when all the data assimilation is already in there?
Yeah. Okay. 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 That is a tough question, I tell you. The reason because you know the answer. So you put everything, for example, you have 4 different kind of approach. You take the simulation into a system, you get the answer. But now you're going to reverse from answer to find out how the issue was contributed, right? You see what I mean? So if you don't have their model, right, use FVCOM to do that. So then it's because different model can produce different results. So you use a simulated result for some model. So then you go back see which turns out important. So use FVCOM. But that's why the problem is, so if you use FVCOM, you don't get the results like they get. You see what I mean? That's why that's a tough question, to be honest. Okay. But if you know if you have a model, you can see if I do the tie and without tie, I see how much they can be changing. So then I can compare the opposition data. Okay, the run model, that's the way. But then assume, we assume that your model is robust, right? For example, you run a ties, if you count the region, you run a tie, you see that's supposed to tie, right? How much tide can be affected, like a temperature, for example. So then you compare analysis result, you say, okay, you see my results different from your one. So that means, partially, what you find is not due to by time. So you compare the wind current simulations around the separator FECOM, you add together, right? Add together, you want to see that. But however, they can run the nonlinear interaction inside the region, particularly for shallow water. It's not a linear system, right? It's not a linear system. Say, how much it contributes tide, how much it contributes current, how much it contributes wind, right? If a linear system, you can do that. But now the system is fully nonlinear. But wind can
And
interact with tide,
and
right?
on top of
Yeah,
that, when the data assimilation is applied,
yeah,
then it's more complicated, right?
yeah,
So
yeah.
I mean, it is hard to tell separating the other components when
That's
the
true.
assimilation is applied.
Yeah,
We don't know which one is which.
that's true. Yeah, yeah, that's exactly what happened. Yeah.
Okay, okay. That
Okay.
that that is his first question.
Yeah. Okay. 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 Sorry. Sorry. I just want to see the. Yeah. Okay. Good. Okay. So now the second question, Dr. Lee can answer because now clock right now. I think
Yeah.
that question be easy, right?
Yeah. So for the second question, O0 to O3 is just the different level of the optimization in the Fortran compiler, no matter J Fortran or Intel Fortran or PJ Fortran. And O0 is the lowest level for the optimization, and O3 is the highest level for the optimization. So the higher the level is, the optimization will make your coding smarter and runs faster. But there are two disadvantages. So the first one would be if you're using a higher level optimization, the compiling time would be increased a lot. And the second thing would be when you use a higher level optimization, sometimes you might make some mistake when you write your coding, and the higher optimization uh, will try to calculate in the way that you do not want it to do. So sometimes the result could be wrong. So we need to be careful when we use a higher level of the optimization. So here I just write two simple example about the optimization. So for the first one, we have a loop from 1 to 1000, and for each iteration a equals b plus 1. So we can directly write it into this way. So in your coding, if you write in this way and compile the coding with say O2, then the Fortran compiler will directly to help you to modify your coding into this one. So it will save you a lot of time because the modern Fortran compiler allows people to use a vector calculation. So this is the second example. So within this loop, we have a sine alpha, but however, this one is the same for all the iterations. So in that way, actually, we can directly first calculate at the beginning and then use this value for each iteration so that we can save the calculation time. So if you compile your coding with the say O2 or O3, so the Fortran compiler will also help you to rewrite your coding and compile it in the smarter way. So this is basically how the optimization does in the Fortran compiler. So there are lots of optimization, and it is different from different version of the Fortran compiler, but basically it will make your coding smarter and cost less time. Yeah.
That's the reason because the operation 就是they have a Fortran program, the program help you to modify your coding to make more efficient run.
Yes.
Okay, but
So
you don't do it by yourself. The compiler will do for you. But then, as Dr. Lee said, sometimes be careful because sometimes
Yes.
it's a high operation. You run the model with two times, because every time they do the operation, they have different way. They do not exactly same. That's why you cannot repeat the result, same result as a two independent run. Okay, even the forcing everything's the same. Okay. Okay,
so
good. So we have
sometimes
lots of question.
We have another one. Professor
Another
Wu,
question.
do
Yeah,
you
lots
have?
of question. Yeah.
yeah,
No,
I'm sorry. So
question. I think
actually
Young,
theoretically O1 and O3 should be same, the
Uh,
computation result. But sometimes it's very different sometimes.
yeah,
yes,
sometimes, yeah, depending on how you write the coding.
yes.
Right? If your coding is very good, the professional writing, you're most similar. But
Mhm.
sometimes you had some people add something, not very perfect writing. That you can see the big difference.
Yes.
Okay. Yeah.
Mhm.
Yeah. We can answer the last question. Yeah. Okay. So this question, so your question, so like so relocation boundary. That's a very good question. So we tell you, the reason we put the relaxation boundary condition, if we find, because your local model, you run it for local forcing, local tie, but you use another model, for example, come from the high count, come from the Nemo other model. So they have a complete different kind of, like a, scale. So also they have a different kind of setting. They also had a different kind of, simulation type of senility for some other. So you probably your solution, compare their solution with their boundary condition, you probably get a gap. You probably get a gap because they're very different. So if you direct put the forcing in, you can get like a pumping, okay, because you get a big difference. You get a pumping like a forcing. You make some kind of no oscillation, perturbation can be happen. That reason we introduce Lagrangian boundary condition is the wave function to consider like the forcing was gradually include the model, include your local model. So then the question, so we use a linear regression round to the in there to put forcing in the outside the boundary. Okay, you will fully use the boundary condition. When they go to the zone, your weight becomes smaller. Then inside the region, you fully use the local forcing, local flare. That's why we can be kind of transition from different kind of dimension model into your local model. Don't make it like a numerical oscillation. But then the question come out, how many layers you need to choose? You need to do testing. For example, normally like East China Sea with the 5 layer working very well, but when you use the 5 layer for the Northeast region, we fail. We completely fail. The reason because they get a lot of inflow from the Northeast region come down, so they got more complete system. So then we found we use the 1 layer, then we get the best solution. No like a transition. Okay, just a direct forcing together. That's why to apply the different case, you need to do testing. Okay, see which one, because we found the global model in the region, around our region, they produce very consistent results on our local model. Okay, that's why you don't want to transition anymore. If you get a transition, you get more problem, right? That's why we use the one layer, okay? Just a transition. But each transparency, we found a HiCom model, they don't include tide when we run that, okay? That's the reason we had each transparency a tide model. We put a low frequency. So because without a tide, the circulation come out a very different case with tide. That's why we had to get a transition, put a low frequency in. That's really depend on location you want to study, okay? Right? So that's why the question two, so you ask the criteria as a good fitting, when origin data available and you got obligation limited or not available. Yeah. So that's why you say that which kind of if I understand it correctly, so you want to ask is you have so many boundary condition, the nesting boundary. So which one you should use, right? That's your question. Yeah.
Yes, yes.
So I don't have a criterion for you to depend on. So if you have data, observation data available, you definitely use the observation data. Okay. If you have observation data, that should be the first choice. If you do have observation sea level data for the boundary, you should use observation data. Then you don't need to use nesting anymore. You just use the boundary condition as nesting boundary. You don't need the relaxation. Don't use the relaxation, use observation data. But however, if you don't have observation data, right? So you should look on your local model, adjust tide to make sure you get a tide correctly. So then you add a larger model inside, but only for low frequency part. But then this one you have to consider relaxation. Also, you can use the called indirect nesting. The most time you use the indirect nesting, the method is no, because you don't want to change anything you already simulating in the locally. You only want to add information the local model missing, right? That's why I use the called indirect nesting. Another with direct nesting, for example, you have a region model, very good model running. So you want to coast in addition model, really small region. You know your boundary condition exactly correctly, not correctly, just good result. That's why you don't need to twin the boundary condition. So you can ties everything in the boundary condition input. You can use the direct nesting. Depend on the case, okay? But time's too short, I probably don't answer the question. If you get more, I can tell you more about this, okay? Okay,
Okay, thank
so
you.
back to you.
Thank you very
So
much.
this is the last question.
Yeah.
So
Also, Dr. Lee has a module developed for this method, nesting method. So if you're interested in has MATLAB module, he can share with you, okay?
yeah, I can send out details about the package. We have a package to convert the HiCom reanalysis dataset to the FVCOM nesting boundary.
Yeah,
Mhm.
he can share with you.
Mm.
Okay.
Yeah.
Good.
Yeah.
Yeah, I think
So
this way, I think Professor Wu's suggestion really good. To collect all questions first, then we can answer together. Okay, they can make
yeah,
it
that's a good idea.
very good. Okay.
Yeah.
Okay, good.
Yeah. Okay, so this is the last question. So thank you so much for everyone joining this discussion. I will post this video record online, and if you are interested, you can check it later and review it. So if you have any question about it, please send us email or post it on the discussion board, and we will see you next week.
Bye.
Bye.
Professor Chen,
Bye.
can I call you after this meeting?
Oh
Just
yeah,
short.
definitely. Yeah, definitely
Yeah.
we can.
Okay. 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 Thank you. Bye.
You want kind of another new zone or
No,
just
no, no. Let me just call you.
call you? Okay,
Phone call.
good.
Yeah.
Okay,
Okay.
good.
Yeah. Yeah. Bye
Okay,
bye.
bye.
Bye bye.